Okay, so good evening, everyone, and I welcome you all to today's live session of Nonlinear Vibration, NOC25 me57. And this course is being taught by Professor S.K. Dwivedi, IIT Guwahati, and I'm Rashya Aditi Ranjan, NPTEL PMRFTA at the Department of Mechanical Engineering, IIT Patna. And we are into the week 7 live session. So, up till now, we have gone through the live sessions for 6 weeks. And every week we have this session essentially to discuss problems which are related to whatever has been taught in the particular week, so that it will be helpful for you all for solving the assignment problems that you get on the portal. Okay, so we'll start with the questions for this week. Okay. Yeah, that's fine. Okay, so coming on to the overview of what has been taught in this week's sessions. So this week was up till now, what we have done is we have discussed about what are the nonlinear systems, how do we identify the nonlinear systems, how do we get the solution of nonlinear system, numerical solutions, analytical solutions, and how to tackle the approximate analytical solutions, and how to find the system response, how to know that how should we deal with the system, what kind of a response a system can give, and everything of that sort. Okay. But up till now, what we have done is we have confined ourselves up till introducing the nonlinearity in the systems in terms of stiffness or in terms of damping or that type, right? Till now, we have studied about free vibrations and forced vibrations. Free vibrations, when there is no external forcing in the system. So what happens is if my system, I consider that my system doesn't have any kind of a damping present in it, right? What is going to happen? Without damping, the system is like if I give some perturbation to the system, damping is essentially responsible for the dissipation of the energy, right? Dissipation of the energy. So if the energy is being dissipated, there will come at, and there is no, regular supply of energy. There is no continuous supply of energy. We just gave some energy initially, and then there's damping present in the system. The energy that has been given initially will damp out, right? It will get damped out, and after some time my system will attain equilibrium position, correct? But if damping is present in the system and there is no external forcing, so if I give a perturbation, the system will go stabilize at an equilibrium point, right? That is the case. But now coming on to what is going to happen if forcing is present. Okay, if forcing is present and if I give some initial perturbation or whatever be the initial condition, after some time the energy that was initially imparted because of the initial condition, it is going to damp out, right? But the energy is that we are giving to the system continuously in terms of forcing function, right? In terms of forcing function, like for example, if I write a system like x double dot plus cx dot plus kx plus alpha x cube is equals to f sine omega t. So what is this? This is forcing. Okay, so what is it doing? It is continuously imparting energy to the system in terms of force, right? It is continuously imparting some energy, right? So now this time, this dissipation is going to dissipate the excess energy which is not continuously being given to the system. But this forcing, the energy that it is imparting, it would always keep my system oscillatory or maybe some kind of a response in a dynamic state. It is not going to come to a static state, right? Because of this forcing which is always present, correct? So in that case, we are going to have different response of the system. We have gone through that system can encounter, quasi-periodic motion, periodic motion, chaotic motion, any of those sort of forcing like kind of behavior can be seen in terms of forcing also. And then limit cycle was also there. Many other things we have seen. Okay. Now this is fine. Okay. Here we have applied a forcing. But then what is a parametrically excited system? Okay, and why is it even important? So when we were discussing about bifurcation, remember, there we discussed that bifurcation essentially happens when there is some change in the dynamics of the system or the static behavior, the equilibrium stretch, when there is the change in the number or the type of the equilibrium points that are present in the system with the change of the parameters, right? With the change of the parameters, right? So we studied about what a parameter is, right? For example, we considered the example of the buckling of a beam. Remember that when we increased this mass was greater than some m, this would lead to what? This would lead to the buckling of the beam, something like this. Okay. So what were we calling m? We were calling m as a parameter, right? So here you can see m will here come here. So here in this equation, in this Duffing equation, m is going to be a parameter, c is going to be a parameter, k is going to be a parameter, alpha is going to be a parameter, f can be a parameter. Likewise, parameter are important. What if these parameter, okay, they are changing with time? What if these parameters are changing with time? Correct. Like here I was having a forcing function, f sine of omega t. Okay. It was not multiplied with my variable, my state space coordinate. It is not multiplied by with x, it is not multiplied with x dot. Okay. But what if it is multiplied? Like for example, if I talk about dielectric elastomer. Okay. So I am doing my research in dielectric elastomer and we work upon finding the equation of motion. So in dielectric elastomer, what happens is I have a elastomer like this. And what do? I apply a voltage. I apply to electrodes over here, right? And then I apply voltage through it. Okay. So this is a dielectric elastomer. These two are electrode. And then I apply a voltage. Okay. So what is going to happen? This dielectric elastomer is going to change its size. Since the voltage is applied in thickness direction, the thickness is going to reduce. Okay. The thickness is going to reduce after the voltage is applied. Okay. The thickness is going to reduce. Now, this decrease in thickness is going to increase in the will lead to, like if I consider that the material is incompressible. Okay. If I consider that my material is incompressible, then in that case, the reduction in the thickness will lead to the increase in the both the lateral directions. Okay. So in that case, when we write the equation of motion, there are various things like we consider the stiffness of the dielectric elastomer, then we consider the damping and everything we consider. Okay, so for now I'll write the equation and also we try to write the equation in terms of lambda, which is the stretch. Stretch means the current dimension divided by whatever the initial dimension was. So lambda is essentially the stretch in lateral direction. Okay, so if I write the equation of motion, it is something like lambda double dot plus some f, which is a function of lambda and lambda dot, minus v lambda cube is equals to, uh, This will not be exactly V. Let us say it is phi is equals to 0. This is some nonlinear function accounting the stiffness, damping, etc. Okay, can you see here phi is a dimensionless voltage. Okay, I'm not going much into the mathematics. What do? We write the equation of motion in terms of voltage, and then what we do? We try to non-dimensionalize the equation. Okay, after non-dimensionalizing, we get phi. Phi is essentially a function of voltage and dielectric permittivity and everything. So this is of something of this sort. So you see phi, which is a function of voltage, is multiplied by lambda cube. Now, okay, if I apply a voltage, constant voltage V, the system is going to what? It is going to attain a equilibrium state. Fine. What if I want my system to have a dynamic state? Okay, like I want my dielectric elastomer to be used as a tactile display. There I wanted to have a sinusoidal oscillation. Okay, at that time I would have to give the voltage as a varying voltage, right? My voltage should be varying. So I'll say that, okay, my voltage is something like V sine omega t. So my phi will be phi naught sine of omega t whole square. There should be a square over here. Okay, this should be the case. So if this is the case, you see that the parameter which is multiplied with lambda cube is changing with time. It is sinusoidal in nature, or to be precise, it is square of the sinusoidal, right? It is changing with time, right? So a forcing or a excitation in the system such that it actually changes the parameter value with time, such that it changes the value of parameter with time is known as the parametrically excited system. Here my parameter is excited. In the above equation, there was a forcing excitation. Okay, the force was getting excited. Yeah, it was changing with time. But now a parameter, in the equation, a parameter value is actually changing with time. There is some kind of a excitation in terms of that parameter, and that is what we call as a parametrically excited system. I hope it is clear. Okay, so this is what it is. Okay, so many physical system, there is parametric, it is parametrically excited. Now you would ask me that why is it parametrically excited and not uh, like why can there not be a forcing excitation? So you see, usually physically in a system, there is always a nonlinearity present, and there is always a continuity of the system, right? We not always consider that, okay, my material is kind of made up of mass and stiffness and everything. Okay, sometimes there are lateral vibrations, sometimes you have to consider about the continuity of the system, we have to consider it as a continuous mass and everything. So at that time, we may get that our parameter is being excited. Okay, and if there is the change of parameter with time, we say that, okay, it is a parametrically excited system. I hope this is clear. Now coming on to resonance theory. So in case of my this system, Duffing oscillator, what was happening? Resonance was happening. When was the resonance happening? So the resonance was happening when my omega was equal to omega n. My forcing frequency, when it is equal to the natural frequency of the system, resonance used to happen. Correct? And this is very common. We have been studying it since a long time now. But what will happen in case of a parametrically excited system? Is it possible that in case of a parametrically excited system also the resonance is going to happen at omega n? No, that is not true. In case of parametrically excited system, the resonance actually occurs away from the, natural frequency, because there is, different resonance condition. Like there is principal parametric excited resonance, and then there is combination resonance, and those things are going to occur because, in a parametrically excited system, firstly we have a parameter which is changing with time, right? And it is not exactly the forcing term. It is getting multiplied with the variable, and then it is causing an effect. And the variable, the state space, is actually changing with time also. Okay, so that is why the resonance condition is different from that of a force excited system. Okay, then after that, uh, Floquet theory was studied, or it was explained that what is a Floquet theory, where is it required, and everything was discussed about Floquet theory. As we will proceed with the question, I have taken a question of the which is related to the Floquet theory. So there I will again briefly explain what is the Floquet theory again. Okay, so as of now, this is what has been discussed, and a few papers were also discussed in the lecture, and I hope that was understandable because I explained it nicely. So we will go now to the questions. Okay, so coming on to question number one. Which of the following is a parametrically excited system? So as I've told earlier also, what is a parametrically excited system? A system in which a parameter is dependent on time or changes with time. Okay, so parameter is not constant. Okay, like initially what we were doing with the forced excited system, we were seeing that okay, for this, like for this kind of a system, my parameters M, C, K, beta, F, these were what? These were constant, right? For a particular simulation, for a particular condition, and for a, if we were doing the simulation, like we considered some mass value, then we considered some damping value, then we considered some beta value, and then we did the simulation, and we found out what was the result. Okay, it was not changing throughout the simulation, but if throughout the simulation, if my parameter is changing, it's a parametrically excited system. So this is a simple question. The first one, we know it's a force stuffing oscillator. Okay, it is force excited Duffing oscillator. Coming on to second, if you remember this, this is nothing but our van der Pol equation, right? So definitely it is not a parametrically excited system. However, there's one thing that is important to understand, that here there is a multiplication of two variables. See here, if you see, we have 1.5 1 minus v square into v dot. So whatever has been multiplied with v, it is actually changing with time. It is changing with time, but it is dependent on the state space coordinate v. Okay, it is not directly dependent on time. Okay, so this is a van der Pol equation. It cannot be said as a parametrically excited system. Coming on to C, yes, it is a parametrically excited system, because you see over here we have x multiplied with pt, where pt is nothing but a function of time. And if you remember, this is also known as the Hill's equation, right? And then option D is also correct. because it has a parameter cos 2t multiplied with x is equals to 0. So this is essentially a parameter which is dependent on time. It is changing with time, and this is known as the Matthew equation. So these two equations are very important because you see, when we started talking about nonlinear systems, we had to, for the introduction of nonlinear system to anyone, what do? We first introduce nothing. We just take the spring mass dashpot model, a linear model, and then we introduce just a beta x cube in it. And we say that, okay, this is how we introduce a nonlinear system, right? That is how we introduced the nonlinear system, right? Now, for a parametrically excited system, the Matthew equation and the Hill's equation, it is like that. When we introduced a nonlinear system, we used the Duffing equation. Now, for introduction of the parametrically excited system, we introduced it with the Hill's equation and the Matthew equation. Okay, it is the basic equation that introduces the concept of parametrically excited system, right? And then what will we do further in the course? We will try to solve the Matthew equation or the Hill's equation, and then we will try to apply it on the further equations. Okay, but these are the two equations that we'll consider to learn about the parametrically excited system. Okay. Coming on to question number 2. For a parametrically excited system, the resonance occurs at. Okay, so I've already told you that for a parametrically excited system, the concept of resonance doesn't apply in the same way as that for a forced excited system, right? It does not apply in the same way. So, for a force excited system, if omega was equal to omega n, resonance used to occur here. Omega is my forcing frequency and omega n is the natural frequency. Okay. But for a parametrically excited system, this is not the case. For a parametrically excited system, there are two cases of resonance, right? The first one is the principal parametric resonance. Okay. So the principal parametric resonance, it says that if my uh, not forcing actually, exciting frequency omega is equal to, let us say, twice of omega n, then this is a case of principal parametric resonance. It could be equal to 3 times of omega n times of omega n is possible. Omega n is the natural frequency of the system, right? It may happen that my system can have multiple natural frequencies. Okay, in that case, twice of omega m, that is also a case of principal parametric resonance. That is why we call it principal parametric resonance. Principal means that there is a multiplication or multiple of the principal resonance. Okay, principal resonance condition for the case of forcing. Okay, so this is the case of principal parametric resonance. Second one is the combination resonance. Now you see, after studying about the subharmonic and superharmonic, this seems pretty understandable, right? That okay, twice of omega n principal parametric resonance is going to happen. It seems quite, acceptable that okay, this can happen and this is fine. Correct? This can happen and this is fine. But if I talk about combination resonance, that is something very different, which we have not studied till now. So what happens is that combination resonance is further of two types. Sorry. One is the sum type, other one is the difference type. Okay. One is the sum type, another one is the difference type. So it says that if my system has two natural frequencies, omega n and omega m, it may happen that the resonance may occur at the sum of the two frequencies, or it may also occur at the difference of the two frequencies. So sum type means omega is equals to omega m plus omega n, and difference type means omega m minus omega n. So you see now it has become more difficult, because earlier for a forced excited system it was very easy for me. It was easy because I had to avoid only the natural frequency. I know the natural frequency. Okay, let us say that the natural frequency is 2. I just have to avoid that frequency in order to get a not a very high amplitude of oscillation. Okay, in order to avoid resonance. But now it has become difficult because now there are multiple ways in which resonance can occur. It could be principal parametric resonance, which is twice of the natural frequency, thrice of the natural frequency, and likewise. It could be combination resonance, where there could be a sum of the natural frequencies can be responsible for the resonance to occur. The difference of the natural frequency could also be responsible for the resonance to occur. So I have to take care of every single case wherein resonance can occur and try to avoid it so as to avoid any kind of a catastrophic failure of the system. Okay, so dealing with a parametrically excited system is definitely difficult, but when we talk about the real world, it comes it is very common that we get the parametrically excited system only. Yeah, there is occurrence of more of a parametrically excited system, correct? Because of the nonlinearities present in the system, because of the actuation way in which it is happening, and considering all those things. Okay, so for a parametrically excited system, the resonance occurs at none here. Okay, coming on to question number 3. Which of the following is a Matthew equation? So I've already told you Matthew equation is x double dot plus delta 2 epsilon sine of omega t. This is your Matthew equation. Matthew equation is one of the most common equation that is introduced on first hand when we talk about parametrically excited system. It is the simplest parametrically excited system you can ever think of. Simplest, but yet it is complex. So you can realize when we go into further solving more typical examples or more difficult examples, it becomes very difficult. Like the research that I am doing, I am also working on parametrically excited system, and becomes very difficult to deal with a parametrically excited system because finding an approximate analytical solution is also very difficult. It is like first we do the perturbation, then we can apply any kind of approximate analytical solution. So yeah, it is very difficult. So this is a very easy question. The first option, as we can see, it is a kind of linear system only, right, with a forcing present in terms of sine of omega t. Second equation, it is a Duffing equation with a softening type of spring. You see there is a minus 5x cube with a forcing function. Third equation, x double dot into something multiplied with x, where that something is having same form like this of that of a Matthew equation. So definitely C is going to be the correct option. Coming on to question number 4. What are the resonance conditions that may occur in a system with parametric excitation with the first 3 frequency modes as 3 Hz, 8 Hz, 21 Hz? Okay, so we have omega 1, If you remember, like I discussed just in question number 2, yeah, that resonance in a parametrically excited system occurs in a different way as compared to a force excited system, right? So if I talk about what can happen, first we will talk about principal parametric resonance. What was that? Omega, some 2 times of omega n could be possible. So if I just apply this, what is going to happen? I can have 3 options of omega: 6, 16, 41. Likewise, you can do for others also. I hope this is clear for you all, right? Second, combination. Further, we have 2 types, sum. What is going to happen in sum? We'll have omega as omega m plus omega n. What are the probable options that can happen? We have 3 frequencies, right? So we'll have omega as 3 plus 8. We can have omega as 8 plus 21. We can have omega as 3 plus 21. This is the sum type. Then we have difference type as well. What is there? In this case, omega m minus omega n. So what are the probable options? We have 8 minus 3, we have 21 minus 8, and we have 21 minus 3 as well. These 3 can happen, right? So this is how you are going to find out, okay? This is nothing in which I should give much time. It is simple maths, plus minus. Okay. So this question says if the eigenvalue of a monodromy matrix is -1 and the steady state response is periodic with time period 16, then the time period of the parametric excitation is. Before solving this question, we should briefly revise about the concept of like what is a monodromy matrix firstly, and how are we going to get the solution, right? How is it possible to get the solution, and how can I even predict just by, like, I just have one value which is the eigenvalue of a monodromy matrix, which is -1, and I have the time period of the steady state solution. How will I tell that what is the period of the parametric excitation, right? So with the introduction of the Floquet theory, it becomes easy. It becomes very easy to deal with the parametrically excited system. So what is a Floquet theory? If you remember, Floquet theory was introduced to talk about the stability, or to talk about how are we going to talk about the stability of a parametrically excited system. Sorry. So if you remember earlier when we used to talk about stability, what were the options that we had? First was, let us do the numerical simulation. Second was that we find out the equilibrium points, and then we find out the eigenvalues, and on the basis of the eigenvalues, then we can say that okay, whether the fixed point is stable, unstable, center, saddle, or whatever is going to be the system behavior, right? But there was one thing that was very clear to us, which was that for a nonlinear system, we do not have a particular theorem. We do not have a theory that could be just applied directly to find out the stability of the system, right? We don't have any particular nonlinear theory. So what were we doing? We were actually linearizing the system. We were using the Jacobian matrix. Yeah, we were using the Jacobian matrix, finding out the eigenvalue, and on the basis of eigenvalue, we were telling about the stability of my equilibrium point. Correct? But what about a parametrically excited system? Because for a force excited system, we find the equilibrium point and then we find out about the stability. But for a parametrically excited system, what should I do? Even if I try to find out the Jacobian, can I find it? Because earlier, when we were finding out the Jacobian for the case of a force excited system, we had to differentiate with respect to the state space coordinate x dot. Here, I have a parameter that is multiplied with the state space coordinate, which is dependent on time, correct? So even if I try to find out Jacobian, my Jacobian is actually time dependent now, isn't it? My Jacobian is essentially time dependent. For example, if I have pt into x, I differentiate it with respect to x, I get pt. So if I have a term pt, which is actually p as a function of time, so for the Jacobian matrix is going to change with respect to time, which was not the case when we were doing what we were doing earlier. My Jacobian matrix was independent of time. It was just having constant values. The moment I used to differentiate and put up the equilibrium fixed value of the equilibrium fixed points, I used to get a Jacobian matrix which is just made up of constant values. Here, that is not the case. That is why Floquet theory was introduced to talk about the study about the stability of a parametrically excited system. So what was my Floquet theory saying? So my Floquet theory said that if I have an equation of motion of the form like this, if I have the equation of motion like this, you see over here, this is a second order differential equation. So if you remember, uh, since the I guess second week only, what we are doing for a second order differential equation, we are converting it into two first order differential equations, correct? We are converting it into two first order differential equations, because of which it becomes a two degree of freedom problem. We have two variables to be taken care of now, two state space coordinates, u and u dot, right? So, and we discussed about the stability using the Jacobian also, where I introduced the concept that like for a two degree of freedom system, I need two independent solutions, okay, in order to write any of the solutions. Okay, like I took the example that if I have a Cartesian coordinate in the x and y direction, and there is a point P which is at a distance of a in the x coordinate and b in the y coordinate, and I want to write P, how will I write? So I've introduced I cap and I introduced j cap, and now I can simply write P is equals to a I cap plus b j cap. So if you see what is I cap and j cap, I cap and j caps are is nothing but the unit vectors in the x and y directions, and these both are independent of each other. So now when I get I and j, which are two independent solutions, I can write the vector coordinate of any of the point in the x and y plane as a linear combination of I and j. Correct. Similar to that, if I have something like this, and if I have two independent solutions, which I can say u1 of t, u2 of t, I can write any solution as a linear combination of these two. Right? I wrote any solution in terms of these two as a linear combination of u1 and u2. Correct? Now, you see this P1T and P2T, this is what? Parametrically excited, changing the value, but it is oscillatory in nature. So for let T be the time period of parametric terms P1 of T and P2 of T. So if this is the time period, what does it mean? It means that P1 at T plus capital T after a single time period, it is going to be the same as P1 of T, which was the initial value. And similarly, P2 at T plus T is going to be nothing but P2 of T. Okay, correct. Now for the equation of motion, if I try to find out how is it going to look if I change my time from T to capital T plus capital T. So U double dot at T plus capital T is going to be what? It is going to be nothing but minus of P1 this. So from the earlier formula, what do we know? We can replace this by like this. So what do we get to know? Like as we have studied in the basic concept of differential equation, that if some value satisfies the differential equation, it means that that value is a solution of that differential equation. Correct? So if my u of t plus t is actually satisfying this equation of motion, it means that u of small t plus capital T is also a solution. U of t plus t is also a fundamental solution of the system. Right? Now, if this is the fundamental solution, then we can relate it. This we can relate with u of t. But how do we relate it? Okay, anyways, it should all anyways be the linear combination, right? So now we try to write it in terms of the linear combination. So we assume that u1 of t plus t is equal to nothing but a11 of u1 of t plus a12 of u2 of t, and u2 of t plus t is equals to a21 of u1 of t, a22 u2 of t. Okay, I assume this. Now what should I do? Okay, we can write it in matrix form. It is very easy now. U1 of t plus t, U2 of t plus t. This is what we got. The reason that we are doing this is that for a parametric, like for the parameter, we know it has a time period of capital T. Now we are trying to convert our equation or our solution state space in such a way such that we can relate our system with the time period, and then we can talk about the stability of the system. Correct? So that is why we are doing it. Now you see that this U1 and U2, it is in our hand, right? We can choose it anything. Whatever we choose as U1 and U2, this matrix is somewhat working as what? A transformation matrix, which is going to transform my state space values at some time t to what the value is after a time capital T. Correct? So this U1 and U2 is in my hands. Whatever value I want to have, I can take. Now see, if you look clearly, I have what? I have U1 and U2 as unknown because that it was I am selecting. Okay? Okay, I have U1 and U2 as a known. So how many unknowns do I have? A11, A12, A21, A22. Four unknowns, right? I have four unknowns. And U1 at T plus T and U2 at T plus T that I can take out either from the equation or I can do the simulation. Okay. Then I can find out the values of this A matrix, all the four values. Anyways, I need four equations to get the value of these four variables. Correct? Now, what do I try to do? Now, you see, we have done it earlier also. The concept of eigenvalues, right? What was the eigenvalue doing? Eigenvalue was able to decouple my equations. Okay. If I know the eigenvalue, this matrix is essentially going to get simpler for me. Why? Because then my equation is going to get decoupled, right? And in that case, my u1 can be written as something which is a constant value multiplied with u1 t. u2 also you can write in that form, right? But how do I try to make this matrix in that way? Well, the best choice is we try to take u1 and u2 in such a way such that this A matrix is a diagonal matrix and the off diagonal terms are 0. In that way, the equation can be decoupled, correct? So it is easy for us, right? We will choose u1 and u2 in such a way that the equation gets decoupled. Now, what is the possible ways in which I can do it? Okay, we'll take it in when we'll solve the question. For now, we'll just assume that okay, u1 and u2s are chosen in such a way that it becomes a diagonal matrix. And in that case, what we can do is we can write this further as v1 of t plus capital T is equals to lambda 1 v1 of t and v2 of t plus t is equals to, okay. Now this solution is known as the Floquet solution. Anyways, now it is easier for us. You know why? See, because here v1 after a time period of capital T is going to be lambda 1 multiplied with whatever the value was at t, small t, correct? So what if I try to find out that what happens after a period of 2t, which means v1 at t plus 2t. This I can write as v1 t plus t plus t, correct? So for this, what I can write? For this, what I can write? This is nothing but v1 of lambda 1 v1 of, this will get converted into t plus t. Again, doing the same thing, we can write as lambda 1 square v1 of t. That is nice. This is something very interesting. It means that if I try to take what is going to happen this to the system after n time periods, I can simply write it as lambda 1 to the power n v1 of t, correct? So if I know the value of lambda 1, I can say that what is going to happen to the system. If I write it in a generalized form for a dimension I can write it as lambda I. So you see, the response after n time periods is nothing but the nth power of lambda I into Vi at t, whatever the response was at small t. So I see that this value, if it is finite, whether the system is going to converge or diverge, it will depend on the value of lambda I, right? It is going to depend on the value of lambda I. So if I have the value of lambda I can say that, okay, what is going to happen to my system? If my lambda I, it is less than 1. So whenever we keep increasing the power of a value which is less than 1, it will tend to what? It will tend to 0 as n tends to infinity. However, if my value of lambda I is greater than 1, what is going to happen? As n tends to infinity, that value is going to go to infinity. That value is going to go to infinity, correct? So now it all depends upon that whether my value of lambda I is actually inside the circle or outside of the circle. Lambda I, it could be complex also. It could be complex also. But then we talk about the absolute value of lambda I. Okay. So if the absolute value of lambda I is inside the unit circle, we say that, okay, it is stable system. However, if it is outside of the unit circle, it is going to diverge with time, right? It is going to diverge with time. So now if I try to write the condition, I have that V of I is equals to what? It will be equal to 0 if the absolute value of lambda I is less than 1, and infinity if the absolute value of lambda I is greater than 1. And we can try to plot it as well. If this is my imaginary axis and this is my real axis, I can draw a circle. So this is the condition of stability. If my absolute value of lambda I is less than 1, then definitely my system is going to get stabilized. However, there is also a case, what if there are 2, 3 or n eigenvalues? Sorry, value of lambda. Then what is going to happen? In that case, if all my values of lambda I is less than 1, definitely system is going to converge to the trivial solution. If any of the single lambda I is greater than 1, the system is going to diverge. Now comes the case, what if lambda I is equal to 1? What if the absolute value of lambda I is equal to 1? Now there are two cases that can happen. First is lambda I is equal to 1. Second is lambda I is equals to minus 1. Right? Now it could be 1, it could be minus 1. So if you look into what happens to when lambda I is 1, if you remember, what was the equation? The equation was Vi of t plus nt was equal to lambda I to the power n Vi of t. My lambda is 1, 1 to the power n. Any power of 1, right? It is going to be what? 1 only. what is interesting is that after every time period, my Vi is again returning to the exact same value, which means that Vi after a single time period, it is going to be Vi of t. After 2t, Vi of t. After 3t, Vi of t, likewise. Okay, this is going to happen. So what do I understand? This case is similar to that of a sinusoid sine, we can say, sine of t. After every 2 pi, it is going to return at the same value. So what do I get to know? I get to know that when lambda I is equal to 1, my system has a periodic solution with time period same as that of parametric term. I hope this is clear. We'll consider this next case in the next slide, which is for lambda I is equals to -1. In that case, what is going to happen? In that case, we have Vi. So what do I get? I get that, okay, Vi if n is even minus of Vi of t if n is odd. Now, what does this mean? This means that Vi after t plus t is going to be minus of Vi of t. Vi after t plus twice of t is going to be Vi of t. Vi after t plus 3t. You can see the value is getting repeated after time periods, after two time period, right? So in this case, again, the system is going to have a periodic solution with a time period 2t, which is twice of the time period of the parameter parameter term. Correct? Okay. So now I know. Apart from this, I'll also tell about the Floquet multiplier, because then we'll solve the question and we'll not go into the theory again. So gamma I, which is ln of lambda I by t, is your Floquet multiplier. And if your Floquet multiplier, if it is positive, then my system is unstable. If it is negative, then the system is stable. What is essentially important to understand is that for a parametrically excited system, we had the stiffness term, we had the damping term. This Floquet theory will be helpful to know whether my system is going to converge to an equilibrium point or the trivial solution, diverge, or is going to have a periodic solution, or is going to have a periodic solution, right? There is also a use of Floquet theory to predict about the stability of a periodic solution. Here we were talking about the stability in terms of a parametrically excited system, correct? But if for my system it is when it is not periodically excited, but then it has a periodic solution, and in that case, how are we going to find out whether the periodic solution is stable or not? Then also we use this extension of Floquet theory. Okay, that I've taken the last question in such a way that there I'll explain it. For now, I hope there is no doubt in the Floquet theory. This is very interesting theory. If I say that for the stability in case of a nonlinear system, this is the only theory that exists because there is no specific stability theory for a nonlinear system. We usually use the Jacobian, we linearize the system, but this is a very nice approach, to deal with a parametrically excited system. Okay. So coming on to the question, now it becomes very easy. So it is saying that the eigenvalue of a monodromy matrix is -1. The thing which we were considering as lambda I, it is nothing but the eigenvalue of the monodromy matrix only. Okay. Okay, monodromy matrix. So for this matrix, if I consider the set of U1 and U2 as 1, 0, and 0, 1, then this matrix, it gets converted into a diagonal matrix, and that diagonal matrix, transformation matrix, is known as the monodromy matrix. So the eigenvalue for monodromy matrix is -1, and the steady state response is periodic with a time period 16. So I have the time period as 16. Then the time period of the parametric excitation is, we know that if the time period is 16, if the eigenvalue is -1, it means that the time period is nothing but twice of the time period of the parametric term. So the time period of parametric term is nothing but 8. This is going to be the correct answer. I hope this is clear. Now it becomes very easy. Now coming on to question number 6, we have the system given as this is, you see, we have the value of u1, u2, u1 dot and u2 dot at 0, and then we have its values at t, where t is the time period. So definitely what do we have to do? We have to apply the concept of Floquet theory, and then we have to find out the Floquet multiplier or the eigenvalue of the monodromy matrix. And on the basis of that, what we can do, we can tell about the stability of the system. Okay. Now I hope it is easy for us to solve because it is just pure mathematics. We have already gone through the concept once again. So we'll just do it very fast. U1 at 0 is nothing but 1. U1 dot at 0 is 0. U2 at 0 is 0. U2 dot at 0 is equals to 1. This is the first set. Second set, we have as U1 as t is equals to 2. U1 dot at t is equals to 3. U2 at t is equals to 6. U2 dot at t is equals to 5. These are the two sets that I have. Now, if you remember, we had a matrix such that U1 at t, U2 at t. It should be small t plus capital T, but here, as it is given in the question, the small t is equals to 0. So we can write it as this: A11, A12, A21, A22, U1 at 0, U2 at 0. This is the first set of equation that I have, correct? So I'll just put the value and see what I get. So I have U1 of 0 as 1 and U2 of 0 as 0. So, sorry, we have these values also. U1 at t 2, U2 at t 6, A11, A12, A21, A22, 1, 0. Now this is very easy because from this we get to know that A11 is equals to 2 and A21 is equals to 6. Coming on the second equation, if we differentiate this equation, differentiating with respect to time, u1 dot at t, u2 dot at t, this is what we are going to get. Also A11, A12, these are not going to get differentiated. Definitely because these are nothing but they are a constant values that have been multiplied with u10, u20 and everything. So when we differentiate, it will be treated as constant. So they will remain, they will not have any kind of a differentiation or anything. They will remain as it is. Okay. Now when we put the values, we have u3 and 5, 0 and 1. So from here, we are going to get A12 is equals to 3 and A22 is equals to 1. So now we can write the monodromy matrix A as nothing but 3, 5. This should not be 1, this should be 5 actually. Okay, this and 2 and 6. Okay. Now what do we have to do? We have to find out the eigenvalues, correct? Because that is how we are going to convert it into a decoupled form. If you remember, in the decoupled form, then we can write the eigenvalue something like Vi is equals to lambda I. Sorry. So lambda I was my eigenvalue, and this was nothing but the eigen direction. Okay. So that is why we need to find out the eigenvalues from which we can get the value of lambdas. Okay. So in order to find out the eigenvalue, we have to substitute a minus lambda I. Determinant of this should be equal to 0, which implies 2 minus lambda, 3, 6, 5 minus lambda equal to 0 is equal to 0. So we'll have 10 we can write it as lambda minus 8 into lambda plus 1 equals to 0. So we have two values of lambda. Lambda 1 is equals to minus 1 and lambda 2 is equals to 8. Okay. So if you see, if we try to plot the this is my imaginary axis, this is my real axis. I have one as minus 1 and the other one as 8. Okay. Now 1 is minus 1. If it would have been just minus 1, then we could have said, okay, it's a periodic behavior, or it's a my system is going to possess a periodic solution with a time period definitely twice of the parametric term. But another eigenvalue is 8, which is far from 1. Okay. So the effect of 8 is going to be dominant. Okay. And in that direction, it is going to take my system towards infinity. Okay. You remember when we discussed about a saddle point where one eigenvalue was positive and the other eigenvalue was negative. So the direction in which the eigenvalue was positive, sorry, negative, the system was trying to converge to the equilibrium point. However, as soon as it came to the equilibrium point, the effect of the saddle direction, the direction in which the eigenvalue was positive, it started getting dominant, because of which, before it could reach the equilibrium point, it actually went to the infinity, right? It is something like if you have c1 e to the power minus 40 plus c2 e to the power 40. As t tends to infinity, this term, it tends to what? It tends to a constant value, right? Because e to the power minus infinity, what is it going to give us? But if we talk about this term, as time tends to infinity, this term goes to infinity. That is just right. This term tends to infinity. So the effect of this term in front of this term is like negligible. System gets unstable. Applying the same concept on this, since my one uh, the value at in one eigendirection is 8, it is going to diverge my system, and hence I'm going to have a unstable behavior. The system is not going to be stable, it is rather going to be unstable. You see how easy it is? We just need to know that what is the value at 0, and then we just need to know what is the value after a time period. And that's it. On the basis of that only, we don't know what the system is, we don't know what the equation of motion is, anything we don't know, but just the values, and we can predict whether my system is stable or unstable. Okay, now coming on to question number 7. Question number 7 asks about the Floquet multiplier of a system with response at t0 and t capital T given as follows. Okay, just a second. Okay. See, the process is going to be the same as the previous question. Only we are going to add a extra step, correct? Only we have to add a extra step, right? So talking about how to write it again, we'll just do it very quickly. Okay. Now, as we know, we can write the equation u1 at t, u2 at t, a11, a12, a21, a22, u1 at 0, u2 at 0. If we put the values, we are going to get 3. Differentiating this equation, With respect to time, we are going to get u1 dot at t, u2 dot at t, a11, a12, a21, a22, u1 dot at 0, u2 dot at 0. Okay, so again putting the values, what am I going to get? 1 minus 2, 0, 1. So after this, I'll get the value that a12 is equals to 1 and a22 is equal to minus 2. Now I can write my monodromy matrix A, which is going to be minus 4 and 3 and 1 and minus 2. Okay, this is going to be my monodromy matrix. Now, in order to find the Floquet multiplier, first we need to find out the eigenvalues. Once we find out the eigenvalues, then on the basis of the absolute value of the eigenvalues, I can find out what the value of the Floquet multiplier. Okay, so for the eigenvalue, I have to do the determinant of a minus lambda I should be equal to 0, which is determinant of minus 4 plus lambda 1, 3 minus of 2 plus lambda should be equal to 0. So from this, I'm going to get the characteristic equation as 4 plus lambda, 2 plus lambda, minus 3 is equals to 0. So from this, I can write it as lambda plus 5, lambda plus 1 is equals to 0. So I'll have lambda 1 as minus 5 and lambda 2 as minus 1. Okay. So anyways, just from the concept that we discussed in the previous question, it is easy to tell that definitely my system is going to be unstable, right? Because both my eigenvalues, if I again plot it, 1 minus 1, I minus I, one is minus 1, other one is minus 5. Okay. Anyways, even if one is minus 1, the other one is minus 5, which is outside of the unit circle, which means that my system is unstable, right? But in this question, it is asking me about the Floquet multiplier, whether it is positive, negative, one is positive, both positive. Okay, so if you remember, my Floquet multiplier, gamma I, was nothing but ln of absolute value of lambda I divided by t. So my gamma 1 is going to be ln of 1 divided by t and 5 divided by t. So if you know that for the logarithmic, if my value is less than 1, then I'm going to have a negative value. If it is greater than 1, then I'm going to have a positive value. And if it is equal to 1, I'm going to have 0. Okay. So my gamma 2 is going to be positive anyways. So the question asks that the Floquet multiplier of the system with response this, the correct answer is going to be 1 positive, because the second one is 0 and 0 is not a positive value and a negative value. 0 is 0. 0 has its own identity. So the answer is going to be 1 positive because we have 5. ln of 5 is going to be a positive value. Okay. We have not gone into computing it. Also, one thing is very important that we don't know the value of t over here. That is why the question was asking just to talk about the uh, about whether the value is positive or negative. Okay, because we don't know the value of capital T. If we would have known the value of capital T, then only we could have been able to calculate the exact values of the Floquet multiplier. Okay. Uh, there's also a thing that I would like to mention over here. Like, you know, we could have find the eigenvalues, and on the basis of the eigenvalues, we could have predicted that, okay, my system is either going to be stable or unstable. Why was the reason that we are studying about the Floquet multiplier? Why was the concept of Floquet multiplier introduced? Well, you see that till now we have this mindset. Eigenvalue positive, unstable. Eigenvalue negative, stable. We have this mindset because of what we have been doing for the linear stability and for when we were calculating Jacobian and everything. Okay, we have this typical mindset. So now when we came to the concept of Floquet multiplier, the concept changed suddenly. Now we are seeing whether the value is inside the unit circle or not, right? So in order to ease that, the concept of Floquet multiplier came into existence. What if I apply the logarithmic of the value? Now it is easy for me because I'm trying to find out the absolute value. If it is greater than 1, the logarithmic is going to always give me a positive value, and hence my system is unstable. If it is less than 1, logarithmic is going to give me a negative value, and hence my system is stable. So now what we can do is we can relate it to whatever we were studying earlier for the linear system, or for when we were perturbing the system, when we are applying the Jacobian, or whatever we were doing. We can now relate it to that. So now we can come with the same concept here also, that okay, I don't need to remember the unit circle or anything. Now what I need to remember is that okay, if my Floquet multiplier is positive, my system is unstable. If my Floquet multiplier is negative, my system is stable. So it becomes easier to remember. Okay, coming on to the question number 8. Okay, for the Matthew equation, we have the equation: the stability and instability region is plotted as shown. Then which of the following is correct? Okay, first let me complete the figure. Firstly, this figure is being taken from the NPTEL lecture. Okay, now coming on to, we have two values, 0.5 and 1.5. So if I draw a line over here and here, okay, what am I going to get? Just a second. I think this is fine. Okay, now if I draw a line like this, and another line like this, and now I name the intersections A, B, C, and D. I hope this is fine. And okay, so this is the unstable region. This is stable, and this is stable. Yeah. Let me check. Yeah. Okay. That's fine. So this is the figure. Now the question is saying that which of the following is correct. Okay. So let us just study read what are the options. So the first option says system is unstable for the value of epsilon 0.5 from 1.9 to A. So it is saying that from here to here my system is unstable, which is not true, because from here to here my system is essentially stable. You can see that this is the stable region. Let us just make a region over here. So this horizontal line signifies stable region. Okay. So from 1.9 to A, my system is essentially stable. So this is incorrect. Option B says system is stable for epsilon 1.5 from C to D. So now this option is saying that from C to D, for the value of epsilon 1.5, my system is stable. But that is not true, because it lies in the unstable region. In fact, from C to D, my system is unstable. And apart from that, for every value, my system is essentially stable. Coming on to option C, which says that system is stable for epsilon 0.5 from 1.9 to A. Now, if you look into this, this is the correct option. Why? Because it is saying that the system is stable from 1.9 to A, which is correct. You see over here, this here, my system is stable. This is the correct option. Now coming on to option D, which says that system is stable for epsilon 1.5 from C to D. Unstable, sorry, unstable. Yeah, this option is also correct, right? But what is the need of this kind of plot? How is it helping me out? You see that from this, I know that what value of omega and epsilon together I have to consider for my system to be stable. Because if it is outside of that value, my system is going to be unstable. Correct? Okay. Now coming on to question number 9. Okay. So question number 9 says the amplitude frequency response of an artificial muscle system is shown in figure below. Okay. Which of the following is correct for an application where any kind of jump in the motion for small variation is to be avoided? Okay. Firstly, okay. Now, first let us talk about what is artificial muscle. Any kind of artificial system that replicates the human muscle or the natural muscle is known as a artificial muscle. Okay. Studying about artificial muscle is important, definitely, considering its practical applications and how it can be useful to actually be used as an alternate to the rigid machines that we use as of now. Now, the question says that what kind of a frequency sweep should we use so that any kind of a jump is avoided? Okay, let us say that I'm moving my hand. Okay, I'm moving my hand and I want to keep it on a surface. Okay, and what am I going to do? I'm going to move my hand and keep it on the surface gradually. What if I keep it at a very high speed? I'm going to hurt myself, right? I'm going to hurt myself because of the impact that is going to happen, right? Similarly, if I'm supposed to make a machine, I'm supposed to make a robot, that is going to, you know, replicate the motion of a human hand. In that case, I want that the motion should be smooth, gradual, same like a how it is happens in a human body. Okay, that's fine. But in a human body, the gradualness of the motion, it is controlled by our brain and the neural signals. However, when we are using artificial muscle, the system is not going to be as intelligent as the neural system of a human. You know, a human is the most smartest control system you are going to see. But we have to make our robot that smart. So what should I do? Now I know that my robot is made up of a soft material. It is going to possess nonlinearity then. If it is going to possess nonlinearity, how am I going to avoid any kind of a jump? The best way is we analyze what the amplitude frequency response. Because we have studied earlier also that there is going to be, a deviation from what a linear system behaves like, right? And that deviation, if then I apply the frequency sweep, that deviation may lead to the jump off or jump down of the amplitude, right? And that should be avoided at any cost for my system to be stable, right? So that is what it is being asked in this question, right? So now if I see the amplitude frequency response, what do I see? Up till this zero value, there exists two solutions of amplitude. One is the trivial solution 0. Another one is a solution that gradually increases with the increase of the value of sigma, right? Okay, further it goes to increasing up till what? Q. After Q also it will keep increasing during the forward sweep. But what if I talk about the backward sweep? That is, we start from here. See, if I try to make the arrow from here, it is not visible. Let us choose some other color. For this forward sweep, it is a continuous variation of amplitude. That too a smooth variation. There is no discontinuity, there is no jump. If I talk about the trivial solution is of no use to me because at the trivial solution, I have a zero amplitude. That is, my system is not showing any kind of a vibration, so it is of no use to me. Now, if I talk about the backward sweep, what is going to happen then? So for the backward sweep, for the trivial case, it is of no use. So if I talk about the non-trivial case, the variation is going to be something like this up till what? Up till the point P. After this, there is going to be a jump till the point Q, and after that, the further down backward sweep is going to take my system like this. Okay, this is the unstable branch. Okay, so you see that during the forward sweep, there is a continuity of the system. System is moving in a continuous manner. But during the backward sweep, till point P, there is continuity, but at point P, there is a jump to the point Q, and the further decrement of sigma would lead to a continuous decrease in the amplitude value, right? Well, that is how it is. Now, if as an engineer, I am supposed to make artificial muscle and then give it a frequency input in such a way that there should be no, jump, then I will always select that the frequency sweep should be positive. I should never go into the negative, like the backward frequency sweep. Even if I am going to the backward frequency sweep, I would try that I stop my system before P. Okay, I should stop my system before P, because as soon as it reaches a point P, even a very small variation is going to create the jump and can even cause the catastrophic failure of my system, which I'm going to avoid at any cost. Okay, so which option is going to be the correct? Option A says the muscle should be used by sweeping up the frequency. Yes, this is the correct option. We can read the other options as well. The muscle should be used by sweeping down the frequency. No, this is not correct. The muscle should be used by sweeping up and down the frequency. No, that will not be the correct option, provided there is a condition that there should not be any jump. If my system is capable of uh, taking up a small jump, then in that case we may consider the sweeping down of the frequency. But if there is no possibility that my system can take up the jump up or jump down, then we should always go for the sweeping up of the frequency. Okay, coming on to question number 10. So this question I have taken just to impart the concept of stability of a periodic solution. Okay, your assignment problem does not have any question of this sort, but I thought that maybe I'll just discuss it because Floquet theory was introduced here. Uh, so as I discussed earlier, Floquet theory was applied on what? It was applied on a parametrically excited system. What were we doing with the Floquet theory? With the Floquet theory, we were trying to find out for my parametrically excited system whether my system was stable, unstable, or it was having a periodic solution. Then there were further two cases for the periodic solution to happen. Okay, that's fine. But what if I have a system of this kind? It does not have a parametric, uh, parameter that changes with time. This is not parametrically excited as of now. But I have a periodic solution. See, if you see in the system, there is no damping present. And it is saying that if we perturb it with the initial condition, this 0 0.1 comma 0, which means that at t0, my x1 is going to have a value of 0.1 and x2 is going to have a value of 0. Okay, then what is going to happen? This is system is not having any kind of a damping, so definitely it is going to possess a periodic solution. So when we try to apply the method of multiple scale and everything, we are going to get the solution. Okay, I'm not getting into what the solution is going to be. I'm just writing the solution. Okay, because there is no point of getting into that because we just want to talk about the concept. So x1 we are going to get nearly equal to 0.1 cos of t, and x2 I'm going to get nearly equal to 0.10075 sine of t. You can see both of them satisfy the initial condition that has been given. So these are my solution of the system behavior. You see, for this particular initial condition, my system is going to have a periodic solution. System will have a periodic solution for the given initial condition. Okay, that's fine. Now, till now we were talking about the stability of a fixed point. That is what we were doing, right? What if I talk about the stability of a periodic orbit? I have a periodic orbit, which is given like this, these three equations. How to know if it is stable or unstable? Question arises that where is it required? So remember when I introduced the concept of limit cycles, I told that for a spring mass system, my amplitude of the periodic solution will depend on my initial condition. If I change the initial condition, the amplitude of the oscillation is going to change. Do you remember that? But in case of a limit cycle, Van der Pol equation, where we studied, the change of initial condition was not changing the steady state periodic solution. Yeah, whatever be the initial condition, whether it is inside the periodic orbit or whether it is outside the periodic orbit, it is always going to bring back my system to what? That particular periodic orbit only, right? Same frequency, same amplitude. So then, if for a given system, which is definitely complicated than the van der Pol equation and the Duffing equation or the spring mass equation, where I cannot even tell about by just looking into the system that how whether my system, whatever the periodic solution it is having, whether it is stable or unstable, whether it is a limit cycle or not. In that case, what do I require? I require to find out the stability of the periodic solution. There, the role of Floquet theory again comes into play, right? Now, you see, initially, we were using Jacobian to perturb my system from the equilibrium point. Now again, I will use the Taylor series expansion to perturb my system about the periodic orbit. Now I will perturb my system about the periodic orbit. Okay, so what will I do? I know x1 and x2. Let us call it as x10, x20. These are my solution. Now what do I have to do? I have to perturb it. So what will I do? I will assume the perturbation x1 of t, then I can write as what? X10 of t plus y1 of t. Y1 and y2 are perturbations. Similarly, x2 of t, I can write as what? X2 of 0 of t plus y2 of t. Clear? Now, earlier when we used to apply the differentiation on the perturbations, since my x10 and x20 earlier were equilibrium points, so its differentiation with respect to time, whether first differentiation or second differentiation, used to be equal to 0. But now since x10 and x20 are periodic orbits, its uh, differentiation with respect to time definitely is going to exist. So in that case, I can write my x1 dot of t as x10 of t dot plus y1 dot of t. x2 dot of t is going to be x20 dot plus y2 dot of t. Okay, these are the differentiations. Okay, that's fine. Apart from that, what do I require? I require this. I require the linearization of x1 cube. So I will apply the concept of what? Taylor series expansion, which says what? If you remember, the Taylor series expansion says yeah, f of x, if we have to, you know, write the expansion around a, what do we write? We write f at a plus f dash at a into x plus higher order terms, but we are just going up to the second term because we need only the linearization. In that case, if I want to write the expansion of x 10 of t plus y1 of t cube, I want to write. How will I write it as? I will write it as, okay, I want this expansion around what? x10. So I'll have f of, sorry, this will be nothing but x10 of t cube plus the differentiation. So the differentiation of cube is going to be what? 3x square, 3 x10 of t square into what? y1 of t. Okay, this is what is going to be my expansion. Now when I try to put it in the equation, so for the first equation, what do I get? I get x1 dot, which is x10 of t dot plus y1 dot of t is equals to, okay. Now, if you see, my x10 and x20 are going to satisfy both these equations. Definitely, because these are the solutions. For a differential equation, its solution is going to satisfy the equation. So what we can do is, we can cancel out this. And then we are going to get what? Y1 dot of t is equals to y2 of t. There should not be a dot over here. Okay. And for the second equation, what do we have? We have x20 of t plus y2 dot of t is going to be nothing but minus of x10 of t minus of y1 of t and minus of x10 of t cube. I think there is a 2 also, 2 and minus of 6 x10 of t square y1 of. Again, my x10 and y10 are going to, sorry, x10 and y20 are going to satisfy this equation also. So what we can do is, we can take this term and this term because it satisfies the equation. So we are going to get the second equation as what? Y2 dot of t is going to be nothing but minus of y1 of t and minus of 6 x10 of t square into y1 of t. So now I have both the equations. I'll just write first equation also. Now this is the perturbed equation. Now you see, my perturbed equation is a parametrically excited system, isn't it? My perturbed equation is a parametrically excited system. This is a parametrically excited. How? Because here this term is actually having a sinusoidal variation. So this parameter, this term which is multiplied by y1 is actually changing with time. Okay. So now what I can do is, I can write it as 0, 1, minus 1, 0, y1, y2. Now what I can do? I can use the OD45 and I can, take two different initial conditions, and then I can use those initial conditions to get the monodromy matrix, and then on the basis of the monodromy matrix, what I can do? I can find out the eigenvalues. On the basis of eigenvalues, then I can say whether my periodic solution is stable or not stable. How? Because if the eigenvalues are coming out to be positive, it means that wherever I'm starting, my system is going to diverge from that value. It is going to go away from that value, which means that my system is actually leaving the periodic orbit, which I considered as the equilibrium point. So my periodic orbit is unstable. If it is turns out to be negative, then I'll say that my periodic orbit is stable. Okay, that is how we are going to use the concept. So what are we going to do now? We are going to use the integrators OD45, and we are going to find out the solution. Like we are going to have two initial conditions which are going to be y initial conditions. I'm going to take as y1 of 0 and y2 of 0, where my y1 of 0 is going to be 1, 0. This, from this I'm going to get what? a matrix which has y1 at 2 pi. This matrix is going to tell me whether my system is, or my, not system actually, I should say that my periodic solution is stable or unstable. Okay, I hope this is clear. Anyways, this concept that I shared just now, it is not very important considering your okay. So this concept is not very important considering to what questions you have for your assignment problem. But I have just tried to, impart you the concept that how the theory of Floquet multiplier is essentially important in order to predict the stability of the periodic solution. So, how the graph is going about the stability. Stability anyways play a very important role in dynamics, whether it's the engineering dynamics or whether it's the nonlinear dynamics, whether we consider the linear system or the nonlinear system. Stability essentially plays a very important role, for the designing purposes. So how the graph is going, first we learned about the linear system. Okay, first we learned about that how for the linear system, we first calculated the fixed points by putting the acceleration and velocity 0. After calculating the fixed points, we tried to plot the graph of x versus x dot, and on the basis of that, we were seeing that whether my system is getting converged at a fixed point or it is diverging from the fixed point. So when it was converging, we said that the fixed point is stable. When it was diverging, my fixed point was unstable. Then we came to the concept of Jacobian, where what we were doing, we had a nonlinear system. We linearized the system using the Jacobian about a fixed point. So first we calculated the fixed point, used the concept of Jacobian, found out the perturbed equation, and on the basis of the perturbed equation, what did I do? I found out the eigenvalues. Okay, and on the basis of eigenvalues, then I could give the conclusion that okay, if my eigenvalue is positive, my system is unstable. If my eigenvalue is negative, system is stable, or the fixed point is going to be a stable fixed point. Whether it is a center, which means we are going to have a periodic solution, whether it is going to be a spiraling in, which means I'm going to have complex roots with negative real part, or spiraling out with a complex root, positive real part, and many other such kind of possibilities we had. Then we came to the concept of a parametrically excited system. Then for the parametrically excited system, we introduced the Floquet theory, on the basis of which we told that for the parametrically excited system, my system was getting stable, or my system was getting unstable, or my system was having a periodic solution with time period equal to the time period of the parameter term, or twice of the parameter term. And now we use the same Floquet theory to predict the stability of a periodic solution. So you see, essentially we were just talking about equilibrium point, but now we are talking about the periodic orbit. Okay, so what did we do? Since Floquet theory is applied to a system which was having, uh, periodic uh, parameters. The parameters were showing a periodic variation. So what did we do for a system like for this question? The system which was having such kind of a equation, and which could possess a periodic solution. What did we do? We took out the periodic solution. We used that periodic solution to perturb my system and convert my system into what? Into a system which has a parametrically excited term, right? We converted it into such form, and now what we have done, we can now apply the Floquet theory in order to predict whether my periodic solution is stable or unstable. Okay, so this is it for today's live session. So anything, any question?
Madam, I have a doubt.
Yes.
Madam, in the resonance condition, principal parametric resonance condition and combination parametric resonance condition,
Mm-hmm.
whether it is necessary that the omega is exactly equal to 2 times of omega n or 3 omega, yeah, or we can say it approximately equal to.
Yes, definitely it is approximately equal. Exactly is not possible in case of a practical system. Okay, there is
Because
definitely some variation.
in the assignment, the options are giving like that. If we have a frequency 20 hertz and The other frequencies are given 41 and 62. So whether the uh, mm, principal parametric resonance occurs at this frequency or not.
See, now you're asking assignment problem, so I cannot answer this question, but I can definitely give you a
Madam,
hint.
madam,
What you can do,
I am not exactly asking the assignment question, but I just related this question, this type of question.
okay, so what you can do is, uh, like what you are trying to ask that can you again repeat the question?
Madam, if the frequency excitation frequency is 20 hertz and
Okay.
the in the options the frequencies are giving like 42 hertz and 63 hertz, then the principal resonance will occur on this or not.
It may happen. What the question is asking, that is important. It may happen. It can happen. See, in practical case, this can happen because in practical case, it is not going to be the exact multiple. Okay, but in the assignment problem, since I also have not gone through the assignment problem, what they are trying to ask, but yeah, it can happen. 61 could be a correct answer, definitely.
Oh, okay, ma'am. Thank you.
Oh, okay, so this is it for today's live session. We'll meet next week. Okay, then, bye, good night, and thank you.